you could. So to work this thing, you want to take a moment down the x-axis because you've got A and B on the x-axis. So I would just put my eye right there and look down the x-axis is what I'd do. What that's going to do is eliminate A and B from the equation so I can solve for the cable force. Once I've got the cable force, then I can much more easily solve for the other reactions at A and B. Okay, so that's my strategy on this one. That's how I would solve this thing. So what I would do then is look right down. I said x-axis. I'm sorry, I mean y-axis there. It's the y-axis. So look down the y-axis. Take moments about the y-axis. So what you would see then would be that slab, that awning, whatever you want to call it, extending out to the left. If you're looking down that y-axis, the slab extends out to the left. And notice how I'm taking that expression for the force. It's got an x, y, and a z component for FCD. The z component is the only one that will cause a moment about the y-axis. So that's the only one I'm showing on this sketch. The y component comes right out of the board towards you. The x component acts in towards, the x-axis. So the components look something like that. The only one that really relates to the moment about the y-axis, though, is the 0.444 FCD, which is the z component. So the x component, I think I might have misspoke on some of those axes. The x component comes out of the page. The y, let's see, no it doesn't. The y component comes out of the page. There we go. The x component is directed right at the y-axis. So neither of those, which I'm showing down here, cause a moment about the y. The only thing that causes the moment about the y is the 0.444 FCD. Okay. So you can just take moments there. You get 27,468, which is the weight of the awning times 1.5 meters. That's going to come around counterclockwise, so that's positive. Then the 0.444 FCD is going to go around clockwise, so that's negative. And that has a moment arm of 3 and a magnitude of 0.444 times whatever FCD is. So that gets you FCD, 30,932. And that's the really hard one to find, I guess. Now, once you've got that, you can multiply it by each of the 3 coefficients there to get the x, y, and z components of FCD. Okay. So if I were doing this, that would be my approach on it. I think that's the quickest way to just knock that out. Now you can do a full-blown vector approach on this if you'd like. Yes, and I'll show you that also. So whichever way suits you is fine. All right. All right, now once I've got that, now I've got to get these other reactions at A and B. I'd probably take a moment about the x-axis next. Okay, so I'd be looking down the x-axis like that. And that's going to eliminate A from my equation. So what I would have then would be the weight in the middle of the slab. It's extending out in the y direction. It's 4 meters wide, so I've got 2 meters there to the weight. And then an additional 1.2 meters to the cable. Okay, and those dimensions are shown on the sketch. So I'm going to get the cable force times its moment arm. That would what? Be counterclockwise positive. The weight times its moment arm, which would be negative. And then I'll have my unknown RBZ times its moment arm. And that's counterclockwise positive. So I'll solve for RBZ 2746. So what we're doing here, we're looking at it down the y-axis first. Basically what you get is a beam extending to the left. Then I come on over and I look down the x-axis, I get a beam extending out to the right. And I can successively then solve for the cable force with the y-axis and RBZ with the x. Now I want to get one more. So what I'd like to get here would be probably RBX. Let's see if we can get that. So to get RBX, how could you look at it to solve for that? We've done both of those so far. Yeah, look down at it, right? Okay. So I guess just by process of elimination, if nothing else, just look down, okay? Now, this time, the sketch will not look like a beam. You're looking down at that rectangular slab now, right down the z-axis. So you're going to get a sketch that looks something like that. Now, this will differ a little bit in that you've got to, you're going to have two components of the cable force that you have to concern yourself with, okay? So you can take moments about the z-axis and you'll get RBX, which is 2575 newtons. Okay. So as we've discussed, what you're doing here, you're just taking the 3D sketch and you're looking down given axes. And in so doing, you're turning that 3D problem into a series of 2D problems. You just need to be able to visualize, you know, to do this. Which, as I was saying, is a handy skill to have anyway, you know, for when you're working and all that. And that's true of the civil mechanical type fields. I wouldn't say it's quite so true for some of the others, you know, like industrial. I wouldn't, you know, it's not quite as big a deal. Some of the bioengineering, chemical engineering, you know, probably not as big an issue. Although, you know, it's always good to have skills, you know, regardless of what you do. Okay. I don't think electrical is that big of a deal either. Okay. I guess the funny thing about work is you end up in work, you're just an engineer, you know, you're basically the commodity you're selling when you're an engineer. I mean, why people hire you is you can figure stuff out, okay? And what the stuff is, you know, it could be about anything, really. I mean, the title isn't quite so important once you start working, you know. I mean, you know, I'm a civil engineer. Most of the work I've done civil related, of course, but I've done pump stations, which is really kind of more mechanical. I've done hazardous materials for a while, really more kind of chemical. You know, you move around, you do different things, so you won't be quite so constrained by your degree, you know. You just migrate and do projects, and they pay you to figure stuff out, whatever the stuff is, you know. So keep that in mind, I guess. All right. So we good with this approach here? Doing all right? All right, and then to finish it off, you got to find the forces at A and then that one remaining force at B, which is RBY. You are given that RY, RAY is equal to RBY. That's part of the problem statement. So you just assume they're equal. You just do a sum of FY, and RAY equals RBY, you know. So you can just do force equations to solve for these last ones. All right, so that's one way to approach the problem. The other way is to go at it using a full 3D vector approach with a cross product. Now, if I were to do that, I'd probably take my cross product about point A. There's 3 unknowns there. Plus, there's a fourth one, RBY goes right through A. So all I'm going to be dealing with are 3 unknowns: the cable, RBZ and RBX. those are the ones that I solve for visually here by using moment equations. So if I do a cross product moment about point A, I'm just going to kick those equations out that I just did visually, and it'll just automatically be generated, okay? So you can always, throw a cross product at these. That'll work, okay? It's fine. I find it to be a little bit of work, it's a little bit of extra computation, you might say. You get lots of terms and all that. It's not quite as quick and easy to do. If you can draw those 2D sketches, it's a little easier, I think, to work through the moments. But you can always do cross products too on the ones that are gnarly, that are hard to work through. Okay. So we're doing all right with that. So if I'm going to do a moment about A, there you go. I'm going to just cross things together. I'm going to have two cross products. I'm going to have the position vector 2C, where the cable's at, which is 3.20, crossed with the force vector. And to that, I would add the position vector from A to B. B's are that one hinge is, times its force vector there, the reactions. And, you can either use a cross product, kind of a determinant form like I've done here. And I mentioned this is just how I learned it, so it's how I do it. You guys, I think, tack 2 extra columns on that and kind of do a little diagonal pattern with lines is kind of how it's taught here at LB, I think, to do those crosses. Or I give you the formula for it too. So, whatever works is fine. Just go ahead and do it, okay? And always remember that if you need to do a cross in this class, you got the dang formula right on your formula sheet. So just use it if you need it. Okay. So there it is. And it's on your formula sheet down bottom left, I think. And what you do 3 crosses. One to the cable force, one to B, and the last one to the center of gravity where the weight's at. Okay. And just put all 3 of those in there and do the cross product process for all of them. You'll come up with a pretty big vector expression there. You'll have a lot of things that zero out. I'm noticing the 0, in that first cross, and then the second one has 2 zeros, so the J component will just totally zero out on that one. So, you're going to get some things zeroing out. Okay. And I've got the whole, result of doing the cross product down there, and you see a number of zeros showing up. And then what you do, you'll pull out all the x's, all the I components, and solve for those, set them equal to 0, add them up and set them equal to 0. Same thing with all the j's, and same thing with all the k's. And that will allow you to solve for the cable force for RBX and RBZ, just like we did visually a few minutes ago. Okay. And then once you got those, you just go back and do the force equations. So you could do this either way. These 3D problems are a little bit, a little involved, a little long, whatever. So they'll take you some time, okay? So we're good with all that? Okay. So I just pull out the x's, the y's, and the z's, and then you can just go ahead and solve it. It looks to me like the y equation first will get you FCD, and then you can do the x and z equations to get the other 2 from the look of it. Now keep in mind there is an extra term down here that I've kind of blocked it out, but it's right there. There are 3 crosses you need to do. One to the cable force, one to the reaction at B, and the last one to the weight at the center of gravity. Okay. And then you just got those 3 equations, solve them out, you'll get RBZ, RBX, and FCD. Okay. And then once you've got those, you can just go back to the 3 force equations to solve for the remaining unknowns. Okay. There are the solutions, but I think you're given those anyway, so it's not that big of a deal. So 30,932 for FCD and 2746 for RBZ and 2575 for RBX. Okay. But I think I gave you the answers for these if I remember right. All right. And then once you got those, you can just do the force equations. And this is the exact same slide I had up 5 minutes ago or 10 or whatever it was. Those are the force equations. Those will get you the last ones. Keep in mind that RAY and RBY are equal to each other. That's given in the problem statement. Okay. All right. We good with that? All right, let's have a look at this thing here. This is actually in your homework section. I think it's problem 291. It might be modified a little bit. If you might have a copy of this on 17A, if I'm not mistaken. Do you have one on 17? And it is this schedule. If you don't, if you might have an older edition of the packet, you may not have this. Does anybody not have this? And it's no big deal to draw it up. That should be on 17A. That's where it ought to be. You should just have a copy of that ready to go. So why don't you solve this out? This is like just a little truss. Let's just be sure we all know how to do this, okay? And you'll get this on the test and all that. It's pretty straight up. There's a very systematic process for doing this one, doing these types of problems. So what are the first things to do here? Yeah, get a free body diagram, find the reactions on the whole truss, okay? So treat the truss as one whole object, find the forces on the truss as though it's like one solid thing, one solid triangular plate or something. You want to find the reactions there and there. So why don't you go ahead and do that? That should take you a minute, if that, okay? So find the reactions on the whole truss. I'm just looking at the ratios on that here. Solve for that one pretty quick, really. Thinking what, a moment about A or something like that? Yeah. That's 1,600 or 16,000. Good question. What do you got on your 17A? I think it is 16,000. Yeah, 16,000 is what it ought to be. Okay. Y'all doing okay on those? Hoping that you're getting somewhere around what, 6,000 to 10,000, something like that. Those reactions. Okay, are those okay? During the reactions, everybody doing okay? 6,000 and 10,000 for the reactions? Any questions on that? I mean, that's how you proceed with that. Yeah, you should be getting right on that, just hoping you can just look at it and say, here's what I gotta do, and knock it right out. Okay. So you're gonna have 16,000 times 3 clockwise, that's a negative, plus 8 RD pushing back. Positive, so RD is 6,000, then a sum of FY to get the other, okay? So that's 6,000, 10,000. You okay with that? All right. So before you start jumping into a truss, you want to know what the reactions are. Okay, that's an important thing. Okay. So that's step one. Next thing I'd probably do would be to get those angles in there, huh? Because when you work through a truss, you got to know the angles. So a little bit of trigonometry there. Arctan. Otherwise known as tangent to the -1. You do that to get those 3 angles for AC, BC, and DC. You want those. And then once you've got those, you do method of joints. Oh, those both are 2 to 4. C's in the middle, eh? Oh, okay, good enough. Okay, so there are those angles. Good with that? Okay. All right, now once you got the angles, you got the reactions, you're good to go. Which joint should we start at here? What are the options for the joints to start at? Yeah, A and D. You can even start at B if you wanted. How about start at joint A and just start working through it, okay? The answers are on page 17 as you're working through it. You just let me know if you got questions or ask your neighbor or somebody. So join A first. And I'm doing this on purpose of, I'm going to get this on the test, so get this figured out. Okay? Start at join A, do a sum of force equation. body diagram I can start with. Okay. Okay, once I worked through joint A, I got AC and AB. I don't think I'd go up to joint C. I don't like to look at that one. It's got too many angles in it. I'll go to joint B or joint D, either one next.
Why did you use 2 over 4 for A instead of 2? Because it's from A to C.
Yeah, it is from A to C.
Not from A to B.
So I'm using 2 over 4 for that trig because C is 4 horizontally over from A. Okay. All right. And then sum of F. What are we going to start with on this one? Probably Y. Okay. What's that now? Question?
Yeah, start with Y.
Yeah. Start with Y because you only got one Y unknown. You got 2 X unknowns, but you only got one Y unknown. Okay. Okay, so do that first, get FAC. Once you know FAC, then you can get FAB. Okay, let's start with sum of FY to get FAC. So what, 10,000? Is it 22,300 and some? 22,300, something like that. Everybody doing okay with that? Getting that thing?
Yeah, that they're 5 off. Is that probably because the angle that I'm measuring at is only to 2 decimal points?
Yeah, it's 4 or 5. Like
so, like I'm getting 22,357 for force AC. This is 23,361. It's probably just an angle. So
general rule of thumb, if you're within a percent of those answers in the book, you're good. So 23,361 and then 20,000. Is that what y'all coming up with? So just sum of Fy equals 0 and then sum of Fx equals 0. We're doing all right with that? Okay. Now I like pictures, okay? So that's pushing, that's pulling. So that's 22,361, and this is 20,000 here. So if that's pushing on A, if AC is pushing on A, what's it doing on C? Which way would the arrow be right at C on that member? It's pushing, yeah. See, it's doing that. And if AB is pulling on A, it's pulling on B. So we got to remember to do that. Turn those arrows around when you get to the other side. It's like, so like think of AB as being like a rubber band that you're stretching apart with your hands. Your hands are the joints. That rubber band's going to be pulling both of your hands in, both of them, okay? Think of AC as being like a block of foam rubber. You're pushing in on it, it pushes both of your hands out, okay? So AC is in compression, it pushes on the joints, and AB is in tension, it pulls on the joints, okay? All right, and then you just kind of keep going through there. I wouldn't go up to joint C because both BC and CD are at angles, which will make them a little bit hard to figure out. So, I went to joint B next, is what I did. You could also go to joint D. So, okay. We're about out of time here, but is everybody good with that? We got any questions on that? Okay. And now, I gave you a couple of those, 242 and whatever the heck it was, 292 and 294, I think?
Yeah.
Yeah. Now, a couple of things. Draw free body diagrams of each joint. List them, your answers, and the answers shown on 19B and C. And the other thing is, do them this weekend. Don't save these for Tuesday night. You don't want to do that, okay? They're due Wednesday. They'll take some time, so try and knock them out this weekend, okay?